In chapter 12, so far, all we've done is talk about how to find the measures of angles in a circle or find the measures of arcs that are on a circle. In this section, we're going to talk about how we can use those same theorems to help us find a relationship between the segments of lengths that are inside a circle, or in other words, how to find the length of a chord inside of a circle. So let's start by looking at the picture that I have here. I've drawn a couple different chords and then I connected them at endpoints. So in this picture, angle R should be congruent to another angle in this picture. And when I look at this, I notice that angle R is intercepting arc QT. Well, angle S also intercepts that same arc. So if you don't remember the theorem, let's just pretend that this arc was 100 degrees. Angle R should be exactly half of that, which would mean it's 50 degrees. But since angle S is also hitting that same 100-degree arc, that means angle S is also 50 degrees. So we don't know the measure of arc QT, but if it was 80 degrees, R and S would be 40 and 40. If QT was 10 degrees, R and S would be 5 and 5. So we don't know what the measurements are, but we do know that they are the same. So we're just going to say that angle R has to be congruent to angle S. And then likewise, if you look at the picture, angle Q and angle T are both cutting off the same arc RS. So that means that angle Q and angle T have to be the same. Well, if I have two angles in triangle RQV, and I'll trace that out here, if I have triangle R to Q to V, that triangle excuse me, has two angles that are exactly the same in triangle SVT. So I know by angle that these two triangles are similar. Not congruent, one of them is possibly bigger than the other, but they are similar. All of their angles match. So let's see if we can write the statement of similarity correctly. If I start with R to Q to V, I'm going from the markings of 1 to 2 to none. So I'd have to go from 1 to 2 to none, which would be triangle STV. Well, if I know that the two triangles are similar, I should be able to create proportions. That was the whole idea of similarity. So I'm going to create a proportion that says this. RV, which is the first and last letter, should be compared to the first and last letter or segment SV. Likewise, QV, which are the last two letters of the first triangle, should compare to the last two letters of the other triangle, which is TV. So that proportion is definitely true inside of this circle. But to solve a proportion, we always say, well, I could cross multiply and say that RV times TV should equal SV times QV. Now let's go back and erase all the stuff on the circle. We used the angles to figure out that these were similar, and that similarity idea ended up giving me that two segments multiplied together should equal two segments of this other circle. So let's look at that. We've got R to V, which is this segment, multiplied by TV, the other part of that entire chord, R to T. And SV is being multiplied by QV, so the chord from S all the way to Q, those two pieces multiplied together should equal the two pieces of chord RT. And that's the theorem that we get from those angles. So it basically boils down to this. If two chords intersect each other in the inside of a circle, then the product of those segments of one chord is equal to the product of the lengths of the segments of the other chord. Now it sounds like a lot in words, but it's basically saying this. If this is the first chord created by parts A and C, if I multiply those two parts together, it should equal the other chord's two parts, B and D, multiplied together. Very simple theorem that comes from the idea of similar triangles if I were to connect the ends of the chords and create triangles. So let's see how we can use this theorem to solve some examples. So here's a couple of very basic examples. First example, 3 and x are on the same chord. So it's the two parts that are on the same chord that should be multiplied together. So 3 times x. And then 2 and 12 are the two pieces of the other chord, so those should be multiplied together. And the theorem says that those two pieces multiplied together should equal the other two pieces from the other chord multiplied together. So I get a very simple equation that says 3x equals 24. So x has to be 8. Very simple. Now I can change this up depending on what lengths that I give you. For example, in the next example, I give you ax equals 3, cx equals 6, but then instead of giving you part bx or dx, I give you all of bd is 11. Well, that changes things a little bit. So if I'm looking for bx, that's what I'm going to call my variable. I'll call it x. I don't know what dx is, like in the last example, but I do know that if x was 4, dx would be 11 total minus the 4, leaving me 7. So I'm going to call dx the full length minus the other part of x. We've used that idea many times before. So now I'm still going to set up my equation. It's the two pieces on the same chord multiplied together. So 3 times 6 should equal the other two pieces of the other chord multiplied together, which in this case would be x times 11 minus x. So setting up the equation, very simple. This equation is a little bit more difficult to solve, but we should be able to solve a quadratic. If you haven't seen the quadratic yet, here it comes. 3 times 6 is 18, but when I distribute the x into this quantity, I'm going to get 11x minus x squared. Like all quadratics, I'm going to make one side equal to 0, so I'm going to add the x squared and subtract the 11x to the other side to get x squared minus 11x plus 18 equals 0. I always try and factor them first, so I'm going to try and figure out two numbers that will multiply to 18 but add up to a negative 11. And I believe those two numbers are a negative 2 and a negative 9, which means x is either 2 or 9. So here's the interesting part about this problem. X is either 2 or 9. So if x was 2, then the other part would be 9, and that would work. 3 times 6 is 18, 2 times 9 is 18. So 2 definitely works. But if x was 9 instead of 2, that would leave me 2 left over for the other piece, and 9 times 2 is still 18, 3 times 6 is still 18. We don't know which part is 9 and which part is 2. So we're going to just put that it could be 2 or it could be 9 depending on how this problem is set up. And we don't go by how the picture looks. We simply say, you know what? It could be 2 or it could be 9. Those are my two answers. And then for the sake of time, I'm going to give you these last two theorems, very simple to use, and I'll give you a couple examples. If you read the theorem, it may not make sense at first, but it pretty much works like this. It says a squared equals b times b plus c. We're basically saying this. If you draw a segment from an outside point, you should always multiply the outside segment times the whole segment, and that will equal the other segment from the outside segment multiplied by the whole thing. So I say it like this, and both of these theorems say the same thing. It's the outside segment times the whole length equals the outside segment of the other one multiplied by the whole length. It just so happens that since A is a tangent, this segment A is the outside part and the whole length at the same time. So it'd be B, the outside part, multiplied by B plus C, the entire length. And that should equal the outside part of the other segment, A, times the whole thing, which is A. And then when you take A times A, you get A squared. So let me do this with numbers, and hopefully it'll make more sense and you see how the theorem works. Remember, it's the outside part times the whole thing should equal the outside part times the whole thing. So let's just say that A was equal to 6 and B was equal to 2. And we want to find C. Well, the theorem would work like this. The outside part of 6 multiplied by the whole thing, which is 6, so the outside part 6 multiplied by the whole thing, which is 6, should equal the outside part of the other segment, which is B, so in this case 2, multiplied by the entire segment, B plus whatever C is, so 2 plus C. So we get this equation here that says 6 times 6 equals 2 times 2 plus C. So when I start solving it, I end up getting 36 is equal to 4 plus 2C, which means 32 is equal to 2C, so C would equal 16 on this example. So to make this work, I got to check. Is 2 times the entire length, 18, equal to the outside part 6 times the whole length, which is 6? Yeah, we get 36 equals 36, and this checks. It works. So that's what the theorem is saying. So what I've done here is shown you both pictures. A lot of times the outside part is obvious. So in this picture, A is the outside part, and the whole thing is A plus B. So A, the outside part, times the whole thing, A plus B, should equal the outside part C times the entire length of that segment, C plus D. That's how that theorem works. You just have to put the numbers into that formula or that theorem. And again, it comes from similar triangles and proportions, but for the sake of time, I'm just going to give you that one. See if you can use it to solve and find missing angles, missing segments inside of circles.